know the 5-number summary quickly and easily. As always, least to greatest. Laura, 1,000 points right there. And let's do this.
I found him. What's he doing? I don't know.
The 5-number summary is the following values.
He's talking to someone.
From least to greatest, min, Q1, median, Q3, and the max. Nice answers. If you put the 5-number summary in the chat, you get 1,000 points. Keep these answers coming.
What is it? What happened?
Hey everybody, class is not over. We're about to jump into this. Okay, we got to take the notes right here. We got all the stuff, video details, office hours. Let's get into it. Okay, so we're starting off strong right here. 242, Stant 201, Chapter 13, homework. Intervals. Okay, let's do the first question. Should be able to get all the homework done and a lot of the quiz. So the first question says, we have an interval and we need to interpret it. So from class today, we got all the great notes from class today. We have the interval interpretation, the I am blank percent confident that the true blank is contained in the interval blank to blank. So if you look at the interval interpretation, we need to talk about how confident we are to start. I like to say I am. That's not the interpretation. Where's the we are? I am 95% confident. Should be here. I'll find it in just a second. Here it is. We are. I like to say I am. It's just the way I say it. I am blank percent confident that the true blank, that's what I say. You can say population or true is contained in the interval blank to blank. So if you look at this interpretation right here on the screen, it's going to be very similar to what my Pearson will write. So let's see which of these looks the most similar. They say 1 is. So 1 is 95% confident. That's very close to I am. So 1 is 95% confident that the truth, and what is the truth? It's going to be that all teens, not from the sample because that's just the estimate. We're trying to understand what percent of teens are online pretty constantly. And we estimate somewhere between 42 to 48%. And we're 95% confident that the truth for all teens is contained in that interval. Make sure to write this down. There are written questions on the test that have you do this. You just say, I am 95% confident that the true proportion of teenagers who are online constantly is contained in the interval 42 to 48. Notice that this is usually where people get stuck. And so you need to know how to write this out. I just say I am. You can say we are, 1 is. I just like to say I am. It's the way I always taught it. Next, we have right here, explain what 95% confidence means. It was actually that other slide that I actually went to is what a 95% confidence interval means. It's that repeatedly making intervals, 95% of 95% confidence intervals will contain the truth 95% of the time. So if we make a bunch of 95% confidence intervals, we'd expect 95% of them to contain the truth. And they do talk for a specific sample size right here. Like if you were to make a bunch of intervals, it's like, like it's the law of large numbers. So let's say like 2% of cookies are burned. Well, in the long run, you'd expect 2% of cookies to be burned if you keep making cookies. One cookie is or is not burned. Just like one interval either contains the truth or doesn't. This interval right here, which I highlighted in pink right there, does not contain the truth. This one does. The green is the truth. So, but over the long run of making intervals, 95% of the intervals are expected to contain the truth. Hey, Nancy, good to see you there. So the answer was A to that one. Good job. And so this one right here is if we did many random samples of this size, they do relate it to a size. I got that wrong yesterday. We'd expect 95% of those intervals to contain the truth. So that's got it. That is the first question. Let's get the whole homework done, right, Nancy? Okay, next question. 5, 4 to 3. And question 2. Reaching out 2 standard errors basically builds a what percent confidence interval? So let's not click the answer. Remember the empirical rule. 68, 95, 99.7. Reaching out 2 standard errors, technically 1.96, basically builds a what percent confidence interval? Reaching out basically builds a what percent confidence interval? 95. And the exact number is 1.96. MuBot's dropping the link for the apps in the chat for us. If you want to get a 95% confidence interval, the exact z-score for it, you have to go to between, and there it is, 1.96. 95.449 is the exact 2. But usually we just do 95 is 1.96. So you can build whatever percent confidence you want. If you want 98, 99, it'll cover that amount of area, or 90, you can get the percent confidence relative to the z-score. The z-score would be based on how confident you are. The bigger the z-score is related to higher levels of confidence, or higher confidence, so you have a bigger z-score. So now it wants us to get the margin of error for a poll. That was a super quick question. Let's put this in the notes. We're already on the next question here. Okay, so 652. And question 3. So the margin of error is everything after the what in an equation. The margin of error is everything after the what in an equation. To get the margin of error, it's everything after the what in an equation. I'll start writing the equation for this chapter. It is on the review 3. If you go to review 3, you will see all the equations. It's also in the notes, but review 3 has all the equations. The margin of error is everything after the what. The margin of error is everything after the what. The margin of error is everything after the what. So if we want to find, it says ME, which is margin of error. It's everything where? Let's see if anyone gets in the chat. Very important to know where the margin of error is in a formula. So it just says solve the margin of error. This is all going to come down to
notation, brother.
The margin of error is everything after the plus or minus. So what this means is we don't need to worry about this. We can just solve for the margin of error. Once again, this is everything after the plus or minus. We're not going to worry about the rest of it because it doesn't say make the interval. It just says what is the margin of error, which is the plus or minus on interval. So make sure you know the margin of error is everything after the plus or minus. So the z-star is based on how confident we are. Since we're 95% confident, that means we need to go to a normal curve and find the z-score that shades the middle 95%. And that is going to be 1.96. If you don't know how to get that, make sure to go to the app page right there. And on the app page, you'd enter in 95 and go to between. This is the normal curve applet. Make sure you've selected everything as I have and go to between and get 95% shaded in the middle with 1.96. How would we find n in this situation? Good question. So what is n? Nancy, let's throw you some points. 5,000 points for that question. So what is n? They say that we are trying to figure out what percent think we're on the wrong track. So the percent that think we're on the wrong track is going to be this. There's the percent that think we're on the wrong track. And then it says what percent think we're on the right track is over here. So how do we find n? That's not going to be used, but we'll highlight it. The z we found. What is n? Technically z star, picked on the level of confidence. So what the star represents, it means relative to whatever confidence the problem tells us. So where is n? Where is n? See if you can get it for more points. It really boils down to notation. Where is n? Take a try. There's only a few numbers left on the screen which haven't been marked. So where's n? I'll answer in about 10 seconds. N is going to be right there. Yep. Nice job, Nancy. Yeah. It's how many people we polled. Does that make sense? That's how many people. Great job, Nancy. We'll throw you some more points. It's how many people we polled. And so all we do now is we go in here. Can't move it down for some reason. We'll go to the side of this. We're just going to solve this equation that we go 1.96 square root of 0.75 times 0.25 over, and then we do 1997. We just solve out the equation. Make sure to do p hat, doesn't matter which order you do it in, times q hat over n square root times 1.96. There we go. There's the margin of error, 0.019. 0.019. There's the margin of error. That's not the full interval, it's just the margin of error. And it means we could be off by about this much from the truth, which is the population parameter. So, I'm 95% confident that the truth is within about this much. So what we saw in our sample is about this close to the truth. Pretty sure that's the right ordering. I think not my favorite way of phrasing it. Here we go. Make a 95% confidence roll. About the same thing we've been doing. So here we go. 11 fought a 2. Question 4. Okay, so make a 95% confidence roll. So what do we have to do in a question like this, Nancy? First step for any question like this, it's like, hey, you got to make an interval. We just did it a moment ago, so what do we got to do? Question says make an interval. What is the steps? You're like, oh man, Brian didn't make a video for this one. It says make an interval. What do I need to do? Leo knows the answer. Notation, brother.
Notation,
All is about
brother.
that notation. Do you see any notation up here? I'll go grab the formula. See what you can find. I'll tell you the rest. They changed the pens on me. So we're going to solve the full interval. Nice job. We already got in right there. The sample size. So that's how many people we spoke to. Good job. Anything else? Yep. And if you know p-hat, what else do you know? So does that make sense? Yep. Double check decimal. I think I'm right? Yeah, it's weird because the numbers, the way they work. That should be that right there. Should be Q hat. And now we know what P hat is also. We still know P hat. We're stuck on something. What is this? Nancy, this is the one people get stuck on. Great job, Brando. And make sure to do as a decimal while solving. At the end, you can convert it. Brando, great job. Let's show you some points. No worries. Good practice. And at the end, convert. So don't do them as percentages yet. Do them as decimals. And then at the end, you can do percentages. That'll cause problems if you use the percentages right now. So what is going to be the Z stars? If anyone can get this another 5,000 points, this is usually where people get stuck and they don't know how to get the Z star. So take a moment. I'll see if you can get it. But this is where people get stuck on these. They say, I don't know how to get that Z star. So what is it going to be? What is the Z star going to be? What is the Z star going to be? Any ideas? Even if you say, I don't know, that's a good answer. And I'll tell you. These are some of my favorite chapters because if you know how to do them, problems are quick. We haven't even checked any conditions yet. We should do random, 10%, and success failure. But yeah. So how do we get these? Brando, you're very close. Make sure to click the between button. Brando, you're right there. I think you've almost done it. So Brando, update your answer, but click the between button. So because a confidence interval looks like, when you make confidence intervals, at least the ones we usually make, which are not a less than confidence interval or lower bound confidence interval, 1.6449. So that's the answer right there. We want to shade the middle 90% of the curve. So it's relative to how confident we are. So that's 90% of the curve shaded. The Z is going to be 1.6449 right there. And we use the applet. Yep. You go to the apps right here and make sure to shade the middle 90% because it says that. The star means relative to the confidence level. So you go to the applet, you put in 90% and make sure to click between. If you click above, it's not going to do the between area for you. You have to click between. So Brando, great work. We'll throw you some more points. We're going crazy on these points these days. It's not Wacky Wednesday, but we earned the effect. So Crash, do it well while I write this out. And from here, it's just putting in the numbers. It's literally just plug in the numbers. Literally. Sometimes people say literally and they don't mean it, but no, it's just plug in the numbers. And then usually I solve out for the margin of error first. Is that rotating guy from Volkswagen? No, that's from Crash Bandicoot. Yeah, I think someone created a crazy meme of him. Crash Bandicoot's a PlayStation game. Is there Dora the Explorer has something? I didn't know that, DD. Yeah, Crash Bandicoot is from a PlayStation game from the mid-90s. He still makes some games. You know what? I don't even know if I've ever played a Crash Bandicoot game. I don't know if I've ever played them. That's the margin of error. I always write the margin of error now, 0.0122. And then 0.521. It's going to ask us to convert this to a percentage, so we'll do that right now. So there's the margin of error. It's 52.1 plus or minus 1.2. So what's the lower and the upper? Go ahead and solve the lower and the upper right now. I'm doing it in my head. See if you can get the lower and the upper. Like, you should know what to do with this step right here. So what's the lower bound and the upper bound? That's 52.1 plus or minus 1.2. So I kind of leave you on some things like, okay, you have to find the lower and the upper bound because that's the interval. Yep, 50.9. Subtract and then add. And go back to here. So 50.9 is the subtraction, and then 53.3 is the addition. I like the decimals at DD right there. I like that. Some points. There we go. We got it right. And then how would we interpret this? We're trying to figure out the percent of Californians who want to move out of state, or the proportion of Californians who want to move out of state. Don't read their answer. I want you to write an answer. We're going to take a moment here. Don't read their answers. Now we're trying to figure out the true proportion of Californians who want to move out of state. Don't read their answers. Don't say A, B, C, or D. I want you to try to write it as though it's the test. And when you get to the test, you'll be like, I've done this so many times. I know how to do it. Someone watching the future is like, I promise you, write this out. You'll get it down. So don't look at their answers. And then we're going to look at our answer and see which answer looks like our answer. We will look at our answer and see which one looks like our answer. Don't look at their answers. Is Mubot not going to say, oh, is it confidence? I got to say confidence in Mubot, and then he'll. I am blank percent confident that the true blank is contained in the interval blank to blank. So try to interpret it right here. What does it mean? So California did a survey and they asked people, are you planning to move out of state? 52.1% of the survey said they're moving out of state. And California is going to take action if more than 50% are planning to move out of state. If they have evidence that more than 50% are moving out of state, they're going to take action, which is the next part of this question. So how do we interpret this? I am blank percent confident. So remember what we built? We built the 90%. I am 90% confident that the true proportion. Oh, and good answers, Nancy. It'll be true right there. Not expect. Expected is kind of like predicted from models. Good answers, Nancy. It'll be true. Or population. Those are synonymous. And nearly perfect. The grader might only take off like a half a point for that. Just change expected to true because that's what we're trying to estimate. We're trying to estimate for everybody. It's kind of expected, but population or true is a better word. So good work, Nancy. Another 5,000 points. Did I already click it? I haven't clicked it yet. So one is, yeah, they should consider it because we have evidence to believe more than 50% are moving out. Nice job, Nancy. One is 95% confident the true proportion of Californians who plan to move out of state is contained in the interval 50.9 to 53.3. Yeah. Not of the random sample because we're trying to estimate the true. Notice how this says the true proportion. Yep. And since the interval is entirely above, we should consider because we have evidence that more than 50%. There we go. Which of the statement is correct about 95% confidence intervals? We talked about this earlier. Making a 95% confidence interval means that 95% of your 95% confidence intervals are expected to contain the truth. Which answer goes with that? A, B, C, or D? It's not D. Which answer goes with that? That 95% of 95% confidence intervals are expected to contain the truth. Like if you keep making intervals, it's probably B. I'm not even going to look. Over the long run, 95% of 95% confidence intervals contain the truth, and about 5% won't contain the truth. The law of large numbers come into play right here in this chapter also. So this question is actually going to get to some of the conditions. Say it with me before it even asks you to memorize. Condition 1. This needs to be a what? Condition 1. This needs to be a what? Random sample. Brando knows right there. It needs to be a random sample. Condition 2. We need to do what? Condition 1, we took a random sample. It looks like they did. It's a poll by UC Berkeley. I'll assume it's random. So we're going to assume it's random. Condition 2, they're asking California residents, do you plan to move out of state? Condition 2, what is condition 2? 10%. Do you think that 5,000 people, let's call it 5,000, is less than 10% of all of California? Which is met, yeah. This 4,527 people is way less than 10% of all of California because we're trying to figure out what percent of California is planning to move out of state. So this is way less than 10% of all of California. Definitely met. Condition 3 is what, though? What is condition 3? And let's remember how to know what condition 3 is. What is condition 3? I got too many things open. Condition 3 is what? What is condition 3? We pause. We pause right here. We're right here. We pause. And what's condition 3? Is it expected cell count? Is it nearly normal? Is it SF? Well, what's going on here? I don't know. We're doing proportions. So condition 3 right now is what? Which one is it? It's categorical. So what's the third condition? It's success failure. Exactly. And that's exactly right. Great job, Nancy. Because it's categorical, we're dealing with, do you plan to move out of state? You're like, but these are numbers. We got a percent. But the question is, do you plan to move out of state? We're asking a categorical question. So with the question being categorical, that means we're doing the success failure condition, which you need at least 10 successes, at least 10 failures. And we have to do it the following way. If you want to double check this condition, the mathematics for this condition are NP hat and Q hat. So when you know the notation right here, yep, you're right, it is met. So this would be P hat right here, and then Q hat is equal to 1 minus P hat, which is equal to 0.477. And then this is N, so N Q hat, N P hat. What are P hat and Q hat basically equal to? P hat and Q hat are about equal to what? Just do a hard round on them. What are these values about equal to? What are these values about equal? Just very hard round on them. They're like, well, that's about what? Just think a hard round. They're basically about equal to what? Because then we're getting 4,527. We're saying it's not equal to this, but we're saying, it's close to this. Does that make sense, Nancy? It's about that. Like, I know it's not, but it's close. It's close. Do you think this is greater than 10? Or do you think it's greater than 10? Do you think that value right there, that NQ hat or NP hat, is greater than 10? 50% of 4,527, which, yes. That is way greater than 10. You could plug in the exact numbers there and find it, but these numbers are way bigger than 10. And because we have at least 10 successes, at least 10 failures, we meet all the conditions. There's a random sample way less than 10%. Now, this gets into confidence and precision. The margin of error for the California intervals moving out of state was this. Would the margin of error be larger or smaller with 85% confidence? Now, if you get to a question like this on the test, I want you to do this with your hands. 68, 95. If you get more confident, the interval gets wider. If you get more confident, 68, 95, 99.7, the interval gets wider. Note to take. If you get more confident, 68, 95, 99.7, the interval gets wider. If you get more confident, 68, 95, 99.7, the interval gets wider. 68, 95, 99.7, the interval gets wider. Starts with a W. 68, 95, 99.7. As you go up in confidence, the interval gets wider. So we're not going up in confidence, we're going down in confidence. 95, 68, the interval will get tighter. It'll be a smaller interval. To be less confident, the interval needs to contain the truth less often, which will have a smaller margin of error. The truth is less likely to be in there. That's that question. So to be less confident, the interval would have to, if the interval is less confident, it'll have a smaller margin of error and the truth will be in there less often. 25, 32, we are rocking and rolling. Brando, Nancy, are you getting this all done? Because we're almost done right here. This is a tricky true-false one. 3 more questions on the homework, then we do some of the quiz. Several factors create a confidence interval. Let's write this down and see if we can solve this out. So with this one right here, when you look at the creation of a confidence interval, the margin of error is going to have the following: plus or minus z star, and then square root p hat q hat over n. Now, this is the standard error of p hat. That's what that quantity is called right there, is equal to square root p hat q hat over n. So this quantity, the standard error, is this quantity right here. So it's just another name for it. Sometimes, like some of the notes even say plus or minus z times the standard error of p hat. That's not s times e times p hat. It literally stands for this full thing. So just be careful. Notation can get confusing. I do agree. I prefer to just write it out and not call it the standard error, which that's its name. That's what it's like to be called. For a given sample size, higher confidence means smaller margin of error. Confidence is directly linked to what now? When it says higher confidence, confidence is controlled by the what of the interval. Confidence is controlled by the what of the interval. Take a look at the equation I wrote. And confidence is controlled by what? So when it says higher confidence, that's going to be controlled by the what in this interval. What controls the confidence? Very important you know this. We'll take a moment. We'll throw some points if you get it, or even if you take a guess. What controls how confident we are? Is it the sample size n? Is it p hat, which is the sample proportion? Is it the z star? Is it q hat, which is the complement of p hat? Is it all the plus or minus controls the confidence? Take a guess, see if you get it. The confidence is directly controlled by what? What's up, RotoWave? RotoWave in the chat. We got so many, I love it. RotoWave classic in the chat. What controls the confidence? And what's your icon, Brando? It looks pretty cool. Thank you, RotoWaves. Good to see you. Confidence is directly controlled by the Z. That's what controls it. It has a star because it's relative to confidence. Higher confidence, if you increase this value, the Z, oh, that's cool. Tekken 8, good stuff. If you make this bigger, what happens to the margin of error? If you make Z a bigger number, it goes from like 2 to 3 to 4 to 5. What happens to the margin of error? So if we increase this, the margin of error will get bigger. It gets wider. So that's false. That's just straight up false. So higher confidence means a wider margin of error. Less precise. Exactly. RotoWave's checking those points. I think RotoWave's got everyone beat. How many points? RotoWave's got like 10 billion points. There we go. RotoWave with 47 hours and 10 billion points. We'll throw you a few more points on there, RotoWave. I like that right there. That is, I think you might be one of the highest point getters in the class right now. So glad people still swing by. I love it. I tell people that. I say people just visit the class to hang out and say hi. It's really cool. I like it. Swing by and just be like, what's up? Thank you, RotoWave. You make my day swinging by. Like, I love seeing former students. Like, and I know RotoWave on campus too. For a specified confidence level, larger samples provide smaller margins of error. So Z star. And if you take this class, or you just, in the future you want to swing by one of these streams, you see me online, just come in and say hey again. Like, hey, what's up, Brian? Especially the more I talk to you, the more I'm like, hey, I remember you. So larger samples. If we increase the sample, we are dividing by a bigger number. So what happens to this equation if n gets bigger? If sample size increases, then margin of error will do what? Which is this whole quantity. The margin of error will do what? If n gets bigger, margin of error, yep, because you're dividing by a bigger number, so margin of error goes down. So that's a fact. Yep, that's a fact. Mathematically. Yeah, dude, swing by. Yes, please, before you graduate. This one's tough. This one gets me every once in a while. I hate the way this one's phrased. Okay. This one is saying, hey, I got this wrong the first semester. I taught this class. Don't tell anybody. It's saying if you have a margin of error of something like this right here, it's fixed. It can't change. It's 0.04. Not going to change. And then we go over here, and you have a Z, because this is part of the margin of error. Remember, the margin of error is P hat plus or minus Z star P hat Q hat over N. So we're just taking the margin of error part of the formula and just saying we solved it. So we're just saying we solved that out. Yep, it is true. Austin was true. And it says larger samples provide greater confidence. So what you'd see right here is it's kind of combining the two topics. Larger samples is controlled by the sample size. So it's literally what a larger sample means. Larger samples and greater confidence is going to be purple. Sure. Yeah, it works. Greater confidence is going to be this. That's horrible. I suddenly went back on my idea right there. We'll go orange. So when you look at this right here, think about it. The orange thing is in the numerator. The yellow thing is in the denominator. So if n is increasing, the equation is going to change, right? Does that make sense? If n is increasing, the equation is going to change. Bigger n, this number is going to change. So what would have to happen here? What's going to have to happen? Because if n is increasing, this is going to go down because of n. So because of n increasing, whoops, wanted the highlighter. Because of n increasing, this is going to go down. So how could we counterbalance this? Well, what we could do is we could increase z. And if we increase z, it's going to be a counterweight. Nancy, does this make sense? This is a confusing one. I do agree. No one said that, but I'm saying it. So if you look, this increasing could be counterweighted by this right here because you're saying this stays at equilibrium. It's a very weird theory question. It's saying that the margin of error is fixed for a fixed margin of error. So what it's saying right here is the margin of error cannot change. It is fixed margin of error. This is not going to change. Well, so it's counterbalancing. It's saying if your margin of error can't change, well, we know if we increase n, margin of error gets smaller, right? We know if we increase z, margin of error gets bigger. That's why I have in the orange right here. If you increase z, margin of error gets bigger, right? If you increase n, that's what the color-coded arrows mean. Like if n increases, margin of error gets smaller. If z increases, margin of error gets bigger. Do you follow me on that? So confidence level is determined by z. If z gets bigger, interval gets more confident and wider. N is the sample size. So if sample size increases, we're dividing by a bigger number and margin of error gets smaller. So here's the thing. If you increase n, you can counterbalance it, like undo that by increasing z. Because remember, increasing n makes it smaller. Increasing z makes it wider. So these two are going to fight against each other. It's like if you hypothetically said z is 2 and n is 2. Do you see how they cancel? But then you say, okay, well, I'm going to make this 20. I'm going to make this 20. Do they still cancel each other? Would this mathematically, if it solves out to me, and this is just, let's say, x right here. So would this still solve out to the same as if I just did this right here? Well, because of the square roots here, we'll change it. Square roots are messy. We'll simplify it to square root of x over 2. Although I need that in square root, I do agree. But now if I do 20 and 20, it's going to solve out the same. So you're kind of counterbalance it. It doesn't quite work like that, but they're counterbalancing it. The z increasing makes it wider. The n increasing makes it tighter. And we've never asked a test question this in depth. We do ask about n. We do ask about z. We've never done like, how about them counterbalancing each other for a fixed margin of error where it can't change? Yeah, so this is true. Not my favorite question, but the first two are great. This one's really easy, though. This one is a way easier one to explain. For a given level of confidence, having the margin of error requires twice the sample size. So if you want to do this right here, and you're saying the z star square root p hat times q hat over n, and you want to do this times 1/2. Well, here's the thing. If you times this by 1/2, can the 1/2, Nancy's right, can the 1/2 just go into the radical like this? Mathematically, does anyone know mathematically, can we just say, well, let's just times this by 1/2 and do this? Can you just do that? Can you just put the 1/2, if you're taking 1/2 the margin of error, you're saying, okay, I want half the margin of error. Can you just put that into the radical and times it by n and say, well, that's twice the sample size? No, you can't. what you have to do is you have to re-express it like this. So that is still 1/2 because it solves out to 1/2. But now you can go in here and do z square root p hat q hat. You can add in the 1 if you want. And then you can do 4 right there. 1's identity, so it doesn't matter. So it doesn't require twice the sample size. It requires 4 times the sample size. This is false. It actually requires 4 times the sample size. You get diminishing returns with samples. Okay, that was a long one. All the true falses, but we're done. It's basically a freebie now that I've done it. But know the equations, know the notation. That's the key to those. Okay, a few more questions. Then let's do some of the quiz. 37, 13, or 12, whatever day it is, or I don't know. Here we go, number 8. A student is considering publishing a new magazine directed at the owners of Japanese automobiles. He wants to establish the fraction of cars in the United States that are made in Japan. I know, me too. The computer output to the right summarizes the result. So, once again, how do you think I'm going to start my sentence? I'm not going to read what they write. I don't like reading their answers. It is D. So how am I going to start my sentence? I'm going to say it here for you on this one, Nancy. Great work, everybody. So how do you think I'm going to start my sentence? When I interpret this and don't read what they say, what do you think I'm going to do? What do you think my first 2 words are going to be that I'm going to say? What do you think the first 2 words I'm going to say are? Take a look at what Mewbots got pinned. And then I'll say the full thing. And practice it, know it. What do you think I'm going to say? You got it, Nancy. 5,000 points. So I'm going to say, I am 95, 90, not 95, 99. I am 99% confident that the true proportion, look up here, P cars Japan, the true proportion of cars made in Japan is contained in the interval 34.06 to 48.44%. So they do it a little bit differently. I am 99% confident that the true proportion of cars made in Japan is contained in the interval. So they didn't do the part in the middle that I do. They went, I am 99% confident that the true proportion of cars made in Japan is contained in the interval blank to blank. So it is D. Totally right. Know how to say it. Know how to do it. Well, that was too easy. Too easy. I am 99% confident that the true proportion of cars made in Japan is contained in the interval blank to blank. Okay, last one right here. We could do the next conference roll homework too. A consumer advocacy group is trying to figure out if the fish are actually the fish that are labeled the fish, the red snapper. So they're going to buy these fish and then open up the packet and have a red snapper expert say like, yeah, that's red snapper right there. So going to be interesting how this goes. Ooh, random, less than 10%, and then poise, which you see they basically have right here. And then you have to know what the success failure condition states, which it doesn't state data has to be binary. Some people miss that on the test. The success failure condition says we need what, which will answer the question whether it's A, B, C, or D. We do pass it. So that kind of narrows it down to B and C. The success failure condition states you need what? At least what? What? Which then they'll answer A, B, C, or D. You can tell me B or C, and I'll tell you which one it is. It means, so the data needs to be categorical. That's kind of an assumption that we have using the condition. So the condition says the success failure condition is only for categorical data, and there has to be at least 10 successes, at least 10 failures. Sample less than 10%, and there are at least 10 successes. Yes, I think that's right. It's not 20 or 30. And there's just barely 10 successes. How many failures were there? A failure is the non-conforming group. We took some notes on this during class. How many failures were there? Take a quick screenshot of this right here. So this was from class. That's the sample size. Good answers, Nancy. That is the sample size. And how many failures were there? Or how many successes were there? How many? Yeah, 12. Yeah, there you go. You got it. There were 10 successes and 12 failures. And X is the amount of successes, which is also equal to NP hat. So, okay, so we know what X is. It wants us to make a 95% confidence, I believe. So tell me the notation. What's the notation? Help me out here. Who's got it? Once again, I do mean this. If you're watching this question right now, highly suggest just pausing the screen here and taking a screenshot of this. Highly suggest it. Because this is the equation up here at the top. And knowing it's very important. Knowing the full equation. and how to solve everything. So what is any of the notation? Who's got it? Because we're stuck. What's A of the notation? Any of it. We're building a 95% conf tool. N, we got N. Okay, we got N. Okay, we're rocking and rolling. Okay, we know what N is. What else we got? Any other notation? P is 12. No, P is not 12. Good guess. Remember, they must be between 0 and 1, Nancy. Good guesses. They must be between 0 and 1. They must be between 0 and 1. Well, they're 10, 12? No, not quite. Not quite. What is the equation for P hat? P hat is equal to what? P hat is equal to that. I think you got it now. Because it's going to be equal to 10 over 22. And that is equal to 0.45. And then Q hat is equal to 0.55. And so there we go right there. And so now we go. And remember, P hat and Q hat must add up to 1. So that's a good way to check. And then we're stuck. And then it just reads, what is, it's 4444555. Okay. 10 divided by, it is, because that's, 45544. And then it's 545454. Okay. Well, we could round it. Sure. So what is the Z though? What is the Z? We'll carry decimal place accuracy on that. 1.96, yep, because 95% confidence. So the Z is 1.96 because 95% confidence. You go here to the applet and you put that in. Make sure to go to your applet, and there you go. It'll give you the answer. So now we just simply go through and solve 0.454545 times 0.5454. 545454. There goes that. Divided by 22. Square root. And then times by 1.96. And it's 20.8. So we get the following. We get. We assume. Yes, exactly for z-scores. Yep. Really? Why is it doing this to me? This thing hates me. Now it won't even scroll down. Thank you, computer. Worked before. Okay. We're going to top of the screen now. 0.4545. That's good. Plus or minus 20.80. And so we just simply add and subtract that. Okay. Here we go. Back to here. And we take the number. 0.454545 plus that. 66.25, 3 decimals, so 663. And then 0.4545 minus the number 20.246. There we go. Should do it. Cross your fingers. Woo! I am 95% confident that the true proportion of actual red snappers that are things that are not actually red snappers is contained in the interval. It's not purchased for the study. It's the actual amount that exists in reality. 24.6 to 66.3. Chickens right there. There we go. I am 95% confident that the true proportion of things that are not red snapper is contained in the interval. Blank to blank. Did people get it? How are people doing? If you notice, a lot of this really boils down to notation. I always say, like, it's notation. It really is, especially for these later chapters. You have to know what the Z-star is. It's based on how confident you are. So we're 95% confident, so we choose 1.96. This chapter's not that bad once you get it down. It's like, okay, I get what we're doing, which I think we've done pretty much, like, I don't think the quiz has many other questions. So hopefully people got those hundreds. Mubot saying good, because good morning. He's trained to say if you say good morning. Oh. Somebody would say good morning to me. I say good morning. I say tired. I say I'm tired. Do a little more. We've got the 17th to 22nd, so we've got a lot of time. It's the 22nd, like 22nd's 2 weeks or a week from 2 days ago. So wait, 22nd. Today is Tuesday. Wait, 22nd is a week from today. Is next Tuesday, right? Yep. So, man, there's a lot of questions on the quiz of this. But we've covered pretty much every possible thing. A lot of them are just like interpreting intervals. Thank you, Nancy, right there, helping out. If the level of confidence increases, the confidence interval gets wider. That's true. It's facts. In a confidence interval, the amount we reach out on either side is called the margin of error. Easy, fun questions. If the margin of error increases, the confidence interval gets wider. Margin of error is plus or minus. If the margin of error decreases and the sample size remains the same, the level of confidence... That's so weird. If the margin of error goes down and the sample size hasn't changed, it would have to be because the level of confidence got smaller. Because it's saying the margin of error went down, but the sample size didn't change. It's a weird way to phrase it. Yeah. Oh, the project? Yes. Do we have it? We have it posted right now, right? Let me go take a look at that. We do full things on the project. Let's go take a look. The project. Step 1 project. I'm almost afraid to say due dates. Yeah, Terry pushes it out. Thank you, Terry. He can push things out to the full class. And there it is, Stats 1 project. Oh, we got so much. Look at all that, Tom. And the rubrics on the Stats 1 webpage, yeah. Mm-hmm. And early bonus by Wednesday the 30th. Oh my gosh. There's the different files you can use. Make sure to do this right here. Here's the rubric. Preview the rubric. Look at all this good stuff right here. All the rubric, everything you got to do, listed out for you. Oh, such a big project. We'll work on this together. We'll work on the project. And so I wouldn't start it yet. And do not cheat. Whatever you do, do not cheat. Whatever you do. And if you go over here, you go to the instruction file over here on the web page. There you go. Here are the instructions for the Stats 1 project. There it is. And here it is right here. There's the due date. We got so much time. And you want to make sure you write everything on your own because there's already been some small issues with cheating, but let's just say this is where people really get in trouble for cheating. The more you write, the easier it is to catch cheating. I know our SI leaders are helping out and they're awesome, but of course they're going to make sure you write your own work and do your own thing. They shouldn't create any sort of like just fill in the blank type things. It should be you have to write your own words, and we make sure we work with them to say like, hey, students need to write out full responses. They need to understand what's going on. It needs to be full, longer response. Like you need to write everything. You can use ChatGPT. Make sure to write your own words. But with that, I think we might head off because we're going to start the in-person office hours. Did everyone get the homework done? We have a full step through of the homework right here in this video. So let's put it right here. Confidence intervals. Homework. Full homework. Definitely next time we'll be doing the full homework. And we've got all the quiz questions. Is there any quiz questions? You're welcome, Nancy. The homework is done. We got it done in like 30, 40 minutes. Went through every topic. Reviewed the notation. Really good video right here, I think. With that, thank you, Brando. Thank you, Nancy. Swing by in-person office hours you want. Adeline, good to see you here. Yes. Oh, yes. There'll be office hours. Let's take a quick peek at that. We'll take a quick. Oh, you bet there will be. Adeline, good to see you in the chat. Let me throw you some points. If you're ready, let's take a quick peek at that chapter. Confidence intervals for the mean. Oh, it's so short. First question says, find the critical T value for 90% confidence with 30 degrees of freedom. You think really hard. You go 1.74. You think even harder, you go 1.71. Got it. And then you go to here, 98% common, you go 2.36. How did I do that? How did I do that? Every T has with it what? Every T has with it what, Adeline? Every single T has with it what? Let me add this to the video. Every single T has with it what? Every single T has with it what? We learned this today. Every single T has with it what? The degrees of freedom. Great job, Douglas. Man, we're seeing everyone here now. Douglas is right. The degrees of freedom. So you have to go to the T applet and ask it the following. You say to the T applet, I have 28 degrees of freedom. And I want to build, we'll do a side-by-side screen right here. I have 28 degrees of freedom. And I want to build, not a snowman today, but a 90% confidence interval. So there's the answer. To 2 decimal places, it's 1.7. The reason I'm able to guess this is because I don't know all the t-scores. I know the z-score is 1.6449. So this next one, I know a 98% confidence interval is 2.3263. 2.3263. With 61 degrees of freedom, it's going to be close to 2.35 or 2.36. 61 degrees of freedom. I hear like a hissing and humming. It's weird. 61 degrees of freedom and 98% confidence. It is two. No, that's probably far off. Oh, it gave it to me. Who follows this? Douglas, Adeline, do you follow that all we're doing is finding the t-score relative to how many degrees of freedom? You put in the degrees of freedom right here. And then you also put in the confidence. And you make sure to shade the middle of the curve on the t-curve, which Mubot has put in the chat. And that'll get you the answer right every time right there. Nice job, Adeline. We'll get a few more right here. So... Hearing a lot of humming. Okay. The next one. So excited people want to get this done. I'm like, get it done. Let's just do it. 53. Do it anyways. The world's at Ben Folds. Here we are with the next one. Describe how the t-curve looks compared to the normal. As degrees of freedom go up, the t becomes more what? As degrees of freedom increase, here's a t with low degrees of freedom, medium, large, and high. As the degrees of freedom go up, the curve becomes more what? As the degrees of freedom go up, here it goes again, the curve becomes way more what? So you can see it visually. This is the t-curve. That's 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 with low degrees of freedom, medium degrees of freedom, higher degrees of freedom, and super high degrees of freedom. As we get more degrees of freedom, the curve becomes more what? Notice it's becoming more normal. It looks just like the normal now. 1.96. That's the z-score, but that's a t-score for the curve. Lower degrees of freedom leads to a much more pushed down. Mr. T says, pitiful, and smashes down the curve. And then it's more normal with higher degrees of freedom. As they increase, it becomes closer to the normal, and it becomes more narrow. You can also see that in the visualization that the curve is becoming more narrow. If you watch right here, this is a wide curve with low degrees of freedom, becomes more normal and less narrow. So the curve becomes closer to the normal. The center does not change, which all of them say, and the curve becomes more narrow. The spread becomes more narrow, and it gets closer to the normal. That should be right there. There we go. This one is going to have us do the conditions. Condition 1. What's condition 1 that we have to solve right here? What is condition 1 for dealing with this data? What's condition 1? This is quantitative data, but condition 1 doesn't change. Condition 1, you know it, you love it. How do we collect our data? What is condition 1? I'll give you the second one. I'll do the second condition. You should know condition 1 for the remainder of the semester, like instantaneously. It can be a simple random. Great job, Douglas. It can be simple random. It can be any sort of random sample, as The Rock would say. It doesn't matter. As long as it's a random sample, it doesn't matter. So any sort of random sample, you're good to go. Now, with that said, what is, I'd say condition 2. 10%. We sample less than 10% of the population. What is condition 3? Pause. We are dealing with the housing market and average loss, and we're trying to estimate the true average loss. So what is condition 3? Pause. What is condition 3? Make sure to pause. What is condition 3? What is condition 3? Anyone know what condition 3 is? Wrong material. Who knows what condition 3 is? We're dealing with the housing market and price. So what's condition 3? You have to think where we're at. We just did random and 10%. We're dealing with price of housing market. So there's hints on the screen. We're dealing with the price of the housing market. So what's the third condition? Price of housing market. What's the third condition? Price. Price is quantitative. What's the third condition? Nearly normal. You got it, Adeline. Because it's quantitative. Yep, nearly normal. Does that make sense? Success failures for categorical, like the things we were just dealing with in the last chapter, is categorical. So this is not success failure. It is nearly normal. And we're not going to do 10 successes failures because that's success failure. So we're down to these two. The data are assumed to be independent. Check the nearly normal with the histogram. You can do that. Check the normal population assumption with randomization. No. Check the normal population assumption with the nearly normal using histogram. Check the, yes. Basically, just see if it's a random sample and all that good stuff. See if it's a random sample and see if the histogram looks unimodal symmetric. So they phrase things weird. Like, look at the data. Does it look normal? Now we have to make the 95% confidence roll. This all boils down to notation, just like with the last question. So when we solve this, I'm going to make it bigger because that's too tiny. Okay. So to solve this out right here, what do we need to do? So here we are. We have to know
Notation, brother.
Here's the equation. We solved one of these at the end of class. Tell me any of the notation in this. Any of the notation. Help me out. What's any of the notation? Go. In the words of Spider-Man 2, go! The Daily Show correspondent who did that, the pizza delivery thing. Standard deviation. You are right. Great job. Standard deviation is S. Nice job, Adeline. What's next? What's next? I think Aziz Ansari, that's his name. Really good comedian. N sample size. What's next? Have you noticed that if you know your notation, Y bar is the sample mean. You got it. Y bar is the sample mean. Y bar is this one. Y bar is that one. So now we're just stuck with T, and then tell me there's one more thing we need to know. One more thing we need to know. So we need T star, and then there's another quantity which is going to help us get that, which was the first question we did on this assignment. Another thing. This is where people get stuck because they're just like, okay, I marked everything. How do I get that thing? DF, great job. The degrees of freedom are n minus 1, which is 35 minus 1 is 34. That means we're dealing with a T with 34 degrees of freedom. And it's going to, what percent confidence are we doing? Because the T star is on a percent confidence. So we're building a 90%. So because of that, we go to the applet. We go to 34 degrees of freedom. And we go 90% confident. And it's 1.69. That should be good. 1.691 extra decimal, because you do between your degrees of freedom and the confidence. Every T has degrees of freedom because it tells you the shape of the T. So 1.691. And now you just plug it in. Really? Equations up top screen. 900 over 35 squared. And I usually solve out for the margin of error first. So 35, clear it, 35 square root. And then 900 divided by this times by 1.691, 257.25. And then 9899. And then we simply add and subtract. So that's the interval without being solved completely. And we simply just add and subtract those numbers. So go back here. And now we just take this number right here. We go 9899 plus that number 10,156.25. 10,156 point. Nearest whole number, okay? And then 9899 minus this. So now 9642. There we go. Oh, I am 95% or 90% confident that the true mean housing loss in the market was contained in the interval blank to blank. Suppose the standard deviation of the losses has been this. Okay, so if standard deviation decreases, what happens to the interval? If the standard deviation decreases, let me mark this question. I think we can get it done. We can get this whole thing done. If a standard deviation decreases, what happens to an interval? If a standard deviation decreases, what happens to an interval? Standard deviation. So if standard deviation goes down, the margin of error does what? Standard deviation is a metric of variation. It'll get smaller because it's in the numerator. Because standard deviation, just think of it as 8 divided by something, then it becomes 2 divided by something. So if there's less variation, because standard deviation is a metric, don't worry, it's just practice. So I think when you see it, you probably just saw me doing it. A morning consult, political. We're gonna finish this homework, and I might be able to find it at Daryl. Daryl, thank you so much. If the standard deviation decreases, the larger standard deviation will now my brain's it's increasing. Adeline, if it had been 3,000, so if it got bigger, emails me something, I'll find it. Yep. And then, or do it in Discord and we can post it for everybody and then you get points for posting in the Discord. Because we got to head over to in-person office hours here in a moment. So a larger standard deviation leads to a wider interval. So I misread it. So a larger standard deviation would increase the width because more variation. A classmate suggests that the margin of error in the interval could be reduced if the confidence interval were changed from 90 to 95. No, that'd make it wider. Because 90, 95, you're going out. No, because, oh my gosh. Change to 90. Yeah, that's true. If you lower the confidence, oh my gosh. If you lower the confidence, it gets tighter. 95, 90, 95, 90, 90, 95. I keep reversing it. Instead of changing the confidence level, would it be more statistically appropriate to draw a bigger sample? Yeah, because if you get a bigger sample will decrease the margin of error. Because if you increase this, margin of error goes down. So that's a better idea. You bet. A larger sample would reduce the standard error of the mean, making the interval more narrow. That is true. The standard error is the quantity that I'm highlighting in yellow. So that is the standard error of y bar equals s over square root of n. That is called the standard error of y bar, which is a metric of uncertainty in the quantity of y bar. There we go. Oh, this is so easy. If we have a sample size of 15, what are the degrees of freedom? Oh, you got this. Sample size 15 for a one sample t. It should say a one sample t. For a sample size of 15 for a one sample t, the degrees of freedom are what? A, B, C, or D? It's 14, n minus 1. Nice and easy. Didn't even mark it. This goes to interpretations. So this one goes to decimals. You can have decimals. The confidence interval only estimates the mean. The sample mean number of species does not have to be a whole number. The population mean literally was our first Kahoot question today. Confidence intervals estimate the population mean. They don't estimate samples. They're created from samples to estimate populations. So saw the last part. Yeah. Confidence intervals do not estimate what a sample is. The sample is an estimate of the truth. So confidence intervals use samples to create estimates of the truth. This last one, we'll speed run it real quick. So if anyone watches the video to the end. 95% of cows studied gain between this to this. That's not how you interpret an interval. You didn't even give your confidence level. So it's not a statement of truth. The confidence interval estimates the confidence interval is for the population mean, not the cows in the study. That sounds right. I don't like the way they phrase it. One is 95% confident that a cow, no, it's about the average for all cows. So the confidence interval is not a single cow, it's about the average of all cows. One is 95% sure that the average weight gain among the cows in the study, no, we're not trying to estimate for the cows in the study, we're trying to estimate the population. So we know what the cows gained in the study. They gained an average of 56, and then we're trying to estimate the truth for all cows, which 56 plus or minus 11 is the truth for all cows. So we know the cows in the study gained this much. We know how much they gained in the study. We're trying to estimate the truth for all cows. The average weight gain of cows fed this supplement will be between this and this 95% of the time. That's kind of close, but the truth does not vary. The average weight gain of all cows does not vary. It's a constant, which the confidence interval is trying to estimate. So it's not that the truth will be in there 95% of the time. 95% of the time, the interval will be containing the truth. That is a really ridiculous way to phrase a theory question. If the supplement is tested on another sample of cows, there's a 95% chance that their average weight gain will be between this and this. No, it's about estimating the truth. These are all horrible. There's a 95%, one knows that another sample will have its no. There's a 95% chance that another sample will have its average weight gain in 2 standard deviations of the truth. Yeah. There's another one that's snowfall. I like the snowfall one better because I think it actually has a right answer. But people should have all the answers now for this one. I do like to put the answers out there. If you watch till the end, I know you might have to pause the video, but I kind of speed ran those. But good stuff. Should get 100 on the homework. We will review it. We will go over it. Till then, bye for now, everyone. Bye.